Hi everyone. Now that we've learned the derivative of e to the x, the next step is to learn the derivative of natural log of x. And the two are very closely related. We're actually going to figure out what the derivative of natural log x is using our derivative of e to the x. So let me turn this into a question. Let's say we have y equals natural log x, and we want to find the derivative of y. And I'm going to call it dy dx. And you'll see in just a second, the reason I'm calling it dy dx instead of y prime, we're going to use implicit differentiation for this. Now, when I look back at the question, I go, well, I want to find dy dx, but y is natural log of x, and we don't know that. That's what we're trying to find. So I need to change this. And what I'm going to do, I'm going to change this from a log question to an exponential this way. I'm going to use an e to the x to cancel out my natural log x. If I do that, what I get is e to the y equals just x. See, now instead of a natural log equation, I have an e to the x equation, and I know how to take that derivative. But it's not e to the x, it's e to the y, and that's why I need to do this implicitly. So we just learned e to the x derivative. We just reviewed implicit differentiation. Let's take the derivative of this question implicitly. So when I do that, the derivative of e to the y is e to the y. Because remember, for every e derivative, you start with the function itself. But then you say, well, that was an e to the y, not an e to the x. I'm doing this implicitly, so I'm also going to get a dy dx there. Now, on the other hand, on the other side of the equation, the derivative of x is just 1. Doesn't matter if it's implicit or explicit. When you take the derivative of an x function, you just do it normally. So, if I want to solve for dy dx, what I would need to do is divide both sides by e to the y. So what I have right now, dy dx, which is what I was trying to find, is 1 over e to the y. But we don't really want our answer in terms of y. We want our answer in terms of x. But fortunately, we have this nice easy substitution right here. I already know that e to the y equals x. So all you have to do is do that substitution. And for our final answer, what we get, dy dx equals 1 over x. Now remember, dy dx in this question is the derivative of natural log x, because my very original question, the y that we just found the derivative for, was natural log of x. So that's what we call deriving a problem, or deriving the derivative of natural log x. But this is what you want to do. You want to remember this. We're at the point where our shortcut for derivatives is knowing them and memorizing them. So from now on, just like you know automatically that the derivative of e to the x is e to the x, you now know from this point on the derivative of natural log x is 1 over x, period. Now, from there, we can do the same thing we did with e to the x. We can apply chain rule. So for example, if you have the natural log of something else, anything else, the natural log of 2x, the natural log of x squared, the natural log of sine x, maybe later on after we've learned the trig derivatives, natural log of anything else. What you get is 1 over whatever that thing is, times the derivative of that thing. And here's a good way to think of it. Natural log is sometimes called the reciprocal derivative. In words, what you do, whatever that box is, you take the reciprocal of that box times the derivative of that same thing. So in the equation part, when I said 1 over the box, the empty box, whatever it is, that's a reciprocal. 1 over something is a reciprocal. And then the chain rule says you have to multiply by its derivative. So the derivative is the chain rule part. The natural log derivative basically does a reciprocal. So let's do a quick example. And you'll see, I think you'll see these are actually pretty easy. We're going to find f prime of x. We're going to find the derivative for this function right here. And what we have is a natural log function. And again, instead of just an x, it's more complicated. It's a natural log of x cubed minus 2x plus 1. So what you do is you can either think of it as kind of a formula or just think of it as the reciprocal derivative. This thing right here is what I'm taking the natural log of. I'm going to take the reciprocal of that thing, I'm going to take the derivative of that thing, I'm going to multiply them together. So the first thing I do is 1 over that whole thing, x cubed minus 2x plus 1, times the derivative of that thing. We'll go piece by piece. The derivative of x cubed, that's 3x squared, that's power rule, multiply by 3, lower the exponent by 1. The derivative of negative 2x is just negative 2. And then the derivative of 1 is 0, it disappears. So what we have is a fraction times a polynomial. What you're really doing here, you're just taking this and just putting it on top. So for my final answer, what I get is 3x squared minus 2 over x cubed minus 2x plus 1. And that's it. So you can see natural log is not a hard derivative to work with either. It's not as easy as e to the x. E to the x is the easiest derivative. Natural log isn't too bad though. If you're taking natural log with chain rule, just do the reciprocal, 1 over whatever that thing is, times the derivative of that thing. And then from here, of course, we can do the same thing we do with e to the x. We can start going with product rule, quotient rule, tangent lines, implicit differentiation, any of the things we reviewed in those first couple sections, we can add questions in for natural log. So let's do a few examples right here. We're going to find the derivative of this function. What it is a quotient rule, because you have a top function and a bottom function, but then I just mixed the natural log in there. So again, we're just combining two things you already know how to do. We just learned the natural log derivative, and now we're combining it with a quotient rule. So when I do this question, when I go to find f prime of x, the first thing I'm going to do is the quotient rule. And I say, you know, when I do the quotient rule, I always draw that really long fraction bar, leave myself a bunch of space. And the quotient rule says the very first thing you do is just take whatever's on the bottom and square it. So I have an x squared on the bottom. And then what I have is the derivative of the top. Now that's what's going to be new for us. I'm going to leave that as like a blank space and come back to it in a second. We have the derivative of the top times the bottom, which is x, minus the derivative of the bottom, that's just 1, that's an easy one, times the top, which is natural log of x squared plus 5. I think we'll square that one off. Okay, so for the derivative of the top function, since that's our new part, that's one of those I might go off to the side and do. So I'm going to squeeze it in here in the bottom, and I'm going to do the derivative of natural log of x squared plus 5. And we'll do it just like the question we did on the last slide. I'll start with 1 over x squared plus 5, and then I'll chain rule it. I'll multiply by the derivative of x squared plus 5, which is actually just 2x. So what I get, and again, we can do the same thing, that 2x basically just jumps on top there. So what we get, and I'll go ahead and just put it into the parentheses here now, we get 2x over x squared plus 5. So that's the quotient rule with natural log. So like that is the derivative. The next step is to clean it up a little bit. So if I multiply the x times the 2x, what I would have is 2x squared over x squared plus 5 minus, we can get rid of the 1 and just put natural log of x squared plus 5. And the whole thing is over x squared. That's a little bit cleaner, but I don't really like the fraction inside of a fraction thing. So there's a couple ways to do it. You could multiply everything by x squared plus 5 and cancel out the little fraction in the first one. You could split it up and kind of put the x squared on each one. I would probably do that. Like if you basically just take that x squared, split it up and apply it to each of those separately, what you get is you would have, let's see here, you'd have 2x squared over, then the x squared will go with the x squared plus 5. That's when I put that x squared into the first fraction, minus, and then you'll have natural log of x squared plus 5 over x squared. And then what happens, the last little cleanup step is those x squareds cancel there. So what I would give for my final answer is 2 over x squared plus 5 minus natural log of x squared plus 5 over x squared. And that's not the only answer. Like there's different ways to clean this up. What's important, what's really the most important thing for you guys is that you got this right here. This is the correct derivative. And the cleanup step is it's nice to do, but what's important is that you got that first step. All right, I have 2 more examples I want to do with you guys. Right here we have a product rule example. So let's find g prime. Now product rule is derivative of the first times second plus derivative of the second times first. So the derivative of the first function, that would be x, that's the x squared. The derivative of x squared would be 2x times the second function, which is natural log x, plus the derivative of the second function. Now this is an easy one. No chain rule or anything, that's just 1 over x. So remember, if you ever have to do the derivative of natural log x, that's just a memorization one. That's just 1 over x, period. And then that's times the first function, which is x squared. So what we get is basically just, for the first one, just push it all together, 2x natural log x plus, and on the second one, x squared divided by x is just x. You know, that x in the denominator will basically cancel out 1x from your x squared. And we get a much cleaner and easier answer than our first example. That's our answer. You could also, if you wanted to, this is an extra step, you could also factor that x out and call it x times 2 natural log x plus 1. Either one of those are fine. You don't have to do that extra step, what I did in green there. Those are both fine. So that was a product rule question, a little easier than our first example. The first one was a little messy. But our third example is a very good one. I want you guys to see this one. And what I'm going to do, I'm actually going to end up working this one out twice because I want you guys to see there's an easy way to do it and a hard way to do it, and really notice the difference so you can get used to starting to look for the easy way. So let me do it first. I'm going to do it the hard way first. And the hard way is to say, okay, well, we just learned this is natural log of something. This is basically a chain rule question. So we say, I'm going to do first the reciprocal of that. Now, this is why I say reciprocal instead of, a lot of times when you see natural log, you think 1 over, but 1 over x minus 5 over x plus 3, it's better to just think of it as a reciprocal. So let's do that. I'm going to do the reciprocal of that, which would be x minus 3, x plus 3 over x minus 5, times, and then the chain rule. Now the problem is the chain rule is the derivative of x minus 5 over x plus 3, which is quotient rule. So all of a sudden this question gets messy. So I'm going to do the derivative of, and remember it's not natural log, I'm talking about just what was inside of it. So I'm talking about just what was in the parentheses right here. I took the reciprocal of that, now I'm taking the derivative of that. So I start by squaring the denominator, x plus 3 squared, and then I do the derivative of the top, which is 1, times the bottom, x plus 3, minus the derivative of the bottom, which is also 1, times the top, which is x minus 5. So if we clean that up a little, I'm going to leave the first part for now, the x plus 3 over x minus 5. And then what you get on the second one, leave the x plus 3 squared, you get x plus 3, and then you distribute a negative 1, you get minus x, and that becomes a plus 5. The x's actually cancel. We get x plus 3 over x minus 5 times, and then it'll be 8 over x plus 3 squared. Now what happens here, we have an x plus 3 on top of the first one, and an x plus 3 squared on the bottom. One will cancel. So I can cancel this x plus 3 with one of those. And what I get for my final answer is 8 over x minus 5 times x plus 3. And that's the answer, and that's fine, but that was definitely the hard way. I'm going to show you a much easier way to do this question. That did work though. If you did it that way, I'm not saying I would mark you wrong or anything. I just really want you guys to think about, a lot of times there's easy and hard ways to do these questions. So let me start that example over. Now remember in chapter 7, we did expanding and condensing. I actually talked about this exact problem right here. I said when you're doing expanding, one of the reasons you might want to do that is to make a derivative question easier. So let's do that. Let's do an expanding problem. What we have is natural log, which is a log, of a quotient, u over v. That can be split up into natural log of the top minus natural log of the bottom. Now when I go to take the derivative, h prime, there's no, well, I mean, there's kind of a chain rule, but the chain rule is just going to be multiplying by 1. You see how much easier these are? The derivative of the natural log of x minus 5 is 1 over x minus 5. And then, yeah, I mean, if you want to, you could say, well, I do the chain rule. I multiply by the derivative of x minus 5, but that's just 1. Minus, and then I do the second one, natural log of x plus 3. So I start with 1 over x plus 3. I can do a chain rule, but the derivative of x plus 3 is just 1. So what you get is just 1 over x minus 5 minus 1 over x plus 3. And that's your final answer. Now the reason the answer looks a little different is because the other answer, 8 over x minus 5 times x plus 3, would be if we found a common denominator and combined those. But you don't have to do that. It's the same answer. And I did that just to show you guys one more time. If you have a complicated log derivative question and you do the expanding and break it up into a bunch of simple logs, the derivative work is a lot easier on that. So keep things like that in mind. That's important.